Below is an equation that represents a widely used formula that many of you may be familiar with. Rate times time is equal to distance, or RT is equal to D. This equation is solved for D, the distance. If we take that equation, divide both sides by R, then on the left side, R over R equals 1, and then we get that T is equal to D over R, or the time is equal to the distance divided by the rate. This equation is solved for T. Likewise, if we go back to the original equation and divide by T, we then get that the rate is equal to the distance divided by the time, or R equals D over T. Now the equation is solved for R. So here's all three equations. They're called equivalent equations. The first one solved for D, the second one for R, and the final equation is solved for T. These are called literal equations. There's more than one variable. We often like to solve literal equations for one of the variables. Or as we often say, we're expressing a variable in terms of the others. Or in the top, we're expressing the distance in terms of the rate and the time. The middle equation, we're expressing the rate in terms of the distance and the time. And in the final equation, we're expressing the time in terms of the distance and the rate. Here's another fairly well-known equation. It's an equation used to find the perimeter of a rectangle, where P stands for perimeter, L stands for length, and W stands for width. The equation right now is solved for P, the perimeter, in terms of the length and the width. Often you'll see problems such as this. There'll be a literal equation, such as the one shown, and the instructions will be to solve for one of the variables. In this case, solve for W. So we apply the distributive property to get that P equals 2L plus 2W. Then, to get the term with W all by itself on one side of the equation, we will add the opposite of 2L to both sides. Now here's where it's a little different than some of the equations we've already worked. Normally, when we add the opposite of something to both sides, it's because there's a like term on the other side that we will combine that opposite with. But here, there is no L term on the other side. We just are doing it so that the 2W is all by itself. So where we have P plus negative 2L on the left side, that's as simple as that gets. So that's the way we write it. And now, in order to get the W all by itself, we divide by 2. But remember, we have to divide the entire left side by 2. And in fact, after we cancel the 2's on the right side, we can leave it like that. The quantity P plus negative 2L over 2 is equal to W. But it's probably more commonly written by dividing both terms by 2 separately and getting that 0.5P take away L equals W, which could also be written 1/2 P take away L equals W. The final two lines we have solved for W, or if you like, we've expressed the width in terms of the perimeter and the length. Here's a type of equation you will most likely see quite a few of in the future. It has two variables, x and y. It is not now solved for either one of the variables, but we've been invited to solve it for y. So, to get the y term all by itself, we'll add the opposite of the x term to both sides, negative 3x. We mark out the opposites on the left side, and we're left with 6 plus negative 3x on the right side. Then in line 2, we apply the commutative property and write negative 3x plus 6. We don't have to do this, but it's customary to write the x term first. Now many of you have probably figured out we're going to divide both sides by 2. And on the left side, of course, 2 over 2 is 1, so we mark it out. And then, sometimes it's acceptable to leave it like this. Y is equal to the quantity negative 3x plus 6 over 2, but often we want to divide both of those terms by 2 separately and express it one of the two ways at the bottom, either as decimals on the bottom left, y equals negative 1.5x plus 3, or on the bottom right, y equals negative 3/2 x plus 3. The final three equations are all solved for y in terms of x. To summarize, when solving for one of the variables in a literal equation, perform transformations as necessary to get the variable all by itself on either side of the equation.